All right, well, let's get started. Yeah, so we're going to talk about harnessing the power of non-determinism for software engineering. LiveFront is indeed a great place to work. Brian gave a really great shout out to us earlier today, so I'm sure you saw that. Both Adam and I work at LiveFront. I'll keep it short. We're a digital product studio based here in Minneapolis, and we love what we do. And on the engineering team, we care a lot about engineering craft and quality. So if that sounds interesting to you, come find one of us. We can talk more about that. Brian also mentioned this. We have a monthly event called TC Hack. Super informal, fun chance to just get together with the community and hack on open source or your own personal projects. So if that sounds interesting, check that out at tchacknight.com and maybe we'll see you there. I'm Sam Kirchmeier. I'm VP of Engineering at LiveFront, and this is Adam. Adam, I'm going to awkwardly hold the mic here for you.
Okay.
Introduce yourself.
Adam May, Director of Engineering at LiveFront.
Awesome. And so we're going to cover 4 things today, 4 topics. The first one is non-determinism. We'll talk a little bit about that, give a definition, kind of establish a motivation for why we're even giving this talk. We put a framework together around just helping us think about how we apply AI tools in our work and in our products. And so we'll share that with you and hopefully you find that helpful. We have some examples to share, just practical examples of where we've applied AI in our work and wanted to share those. The section is called Striking a Balance because really we fall a little bit short of fully embracing non-determinism sometimes. And so this is all about where we're making those compromises. And the last section, Adam will kind of wrap up with an example of where we really have fully embraced it with very few constraints. So that is our agenda. Let's start with non-determinism. Here's the definition from Wikipedia. A non-deterministic algorithm is an algorithm that, even for the same input, can exhibit different behaviors on different runs. So basically, you give it the same input. Uh-oh, that's still on. You give it the same input, you might get a different output. This is a classic example of a bug due to a race condition, and this is due to non-determinism. The problem here is that the instructions operate in an undetermined order, and so in run number 1, everything's fine. You get the right bank account balance. In run number 2, you get the wrong bank account balance. We run into this sort of thing as software developers pretty early in our careers. This is something we confront, and at first it's like, it's kind of confusing, but not the end of the world. There's a solution to this. One solution is you could use a transaction. You could use a transaction to just enforce that the instructions always occur in the right order. But there's a cost associated with that, and the cost is it's hard to understand. You have to figure out what transactions are, how they work. It adds complexity to your code base. We tend to start associating things like race conditions and other non-determinism, which Adam will talk about a little bit more here in a minute, with hard things in computer science, and that's for good reason. On the flip side, kind of meanwhile, this is our comfort zone. We love determinism. We want, when an algorithm runs, we give it an input, we get the same output. We can write a unit test for that. Will we write a unit test for that? Maybe, but can you? Definitely. And so this is where we like to be. And what does this have to do with AI? Well, AI is just inherently non-deterministic. So this is comfort zone adjacent, potentially. There's something for us to consider here in our application of this to our work. And coupled with that is just an enormous amount of hype. And we're all dealing with this. This has had a huge impact on just our day-to-day work. The promise of these tools is that we'll get a 10x developer increase. We'll be able to do the same amount of work with fewer people. We'll save a ton of money. And there's kind of a pressure to figure that out and do that. And we've been working on that at LiveFront. And we've had a pretty, I would say, universal or similar experience to probably you when you use these tools. They don't always do exactly what you might consider helpful. Sometimes you spend a lot of time cleaning up a mess that they create. And this kind of problem or challenge, sorry about the mic noise here, it really is interesting. It's just a fascinating problem. How do we best apply these tools to get the biggest advantage that's possible? And so another thing you kind of realize as you're experimenting with these tools and integrating them into your work is that some problems seem like AI is better suited to solve than others. And so the framework we put together, and what we'll show you here, Adam will show you in more detail, is just a way we think is helpful to kind of think about how you might evaluate problems as you're encountering those. So we'll move into that section next. I'll pass it over to Adam here.
Just like hang on to that.
Maybe, I wonder if it'd be better to hang on to that.
All right. Yeah. So, like Sam said, we sort of came up with this idea for how you actually go about choosing problems for AI to solve instead of just sort of using it for everything. And the framework, I think before I kind of dive into that, I kind of want to go through sort of maybe thinking back to maybe when you first started using these tools and your first prompt. If you were like me, you probably thought like, okay, let's just start building something with this, right? So you ask AI to write some code, maybe you run the code, and a lot of times it will just fail spectacularly, right? I think this is kind of a common experience a lot of folks have had. Then you try to point out the problems and ask the agent to fix it. And it says something like, oh yeah, you're absolutely right, like really good, great catch, like, and then proceeds to make the same mistake like 10 more times or 10 different other mistakes that you now have to catch. And it's just like insanely frustrating, right? Like to the point where you pretty much want to just like throw it out the window. So that feeling like I just want to kind of explore what is that, and I think if kind of allow me to self-diagnose a little bit, it's just this kind of idea of cognitive dissonance, right? You have these two conflicting beliefs that you're trying to reconcile, and it just creates this psychological discomfort. And that's getting back to kind of what Sam was talking about with relationship to determinism, which is really, if you think about it, has been an important part of our tools since the dawn of computing, versus, sorry, I think I lost a bullet point there. There we go. Nondeterminism, which is often seen as a bug, like in the example Sam showed with the accounting. So I think back to, kind of supporting that point, this is maybe some image some of you may recognize. This is Grace Hopper's notebook from 1947. She's working on the Harvard Mark II, and someone found a literal moth stuck in a relay, and so she taped it in her notebook. It's like first actual case of bug being found. Right, that's an example of non-determinism that's definitely causing a problem. Versus like a tool maybe some of us use every day, which is like a compiler. Incredibly complex, but deterministic, right? Like if you give it the same inputs, it's going to produce, hopefully, the same outputs, unless there's a bug. And you rely on that to do your job effectively. And so that's kind of the problem, right? Is that LLMs just don't behave the same way as compilers. They're non-deterministic. And there are several reasons why that are just inherent in the design of how they work, and I'm not a machine learning expert, so I'm going to do my best to kind of explain that, but it has to do with several different factors, including token sampling, so the actual prompt you're providing it effectively gets sampled before it's run through the model. There's also an intentional factor, randomness factor, called temperature. You can actually adjust this on some models to try to lower it. You can even lower it all the way down to 0. But in actuality, even if you do that, there's still non-deterministic calculations going on underneath the covers, something called floating point non-associativity, which I'm not going to explain because I'm not a mathematician and this is not a math talk. But I highly recommend, there's like a white paper in our references that kind of goes into some detail about this, and it is pretty interesting. But that's not really what I want to focus on. I think I want to go back to this idea of the cognitive dissonance and how you kind of work through that. I think one of the first things I thought was like, well, maybe it's me, like I'm just using the tools wrong. Like I need to maybe improve my prompts. Like I get the right prompt, it'll just do what I want. Maybe you need to use all the new sort of fancy bells and whistle, MCP, RAG, subagents, Claude skills. I feel like there's a new one coming out every 2 weeks, and some new blog post that says, oh, I need to be using this thing. I think that there's value. I don't want to say don't explore these ideas and try to improve your skills, but I think it's also worth asking, maybe it's the problem that's the problem. The tools will continue to get better, and we're going to get better at using those tools. But right now, I think what we've learned in a very short time is that there are certain problems the tools are already good at. So it comes down to like, how do you choose? Like, how do you choose which problems to tackle? And that's where we kind of started to think about the various examples that we've had at Livefront, and came up with this idea of tolerances. So basically looking at 2 different factors to consider when you're thinking about problems to use AI for. So the first one, I'm going to roll through these pretty quickly, but tolerance for ambiguity, which we're defining as, is it acceptable or even desirable if there are multiple right answers? And right is in quotes because it's entirely up to you to define what correctness means in the context of the problem. And then tolerance for risk, which I think is a little more straightforward, and that's just, what's the impact of a wrong answer? What are the consequences? Like, what goes wrong and how do you recover from that? Serendipitously, a couple weeks ago, as we were putting together this talk, Martin Fowler was on a really good podcast that's super interesting about this exact topic, talking about AI and software engineering. And I loved this. He brought up this idea that his wife is a structural engineer, and she's always thinking in terms of tolerances, because I mostly know what the properties of wood or concrete or steel are, but I've got to go for the worst case. We need probably some of that kind of thinking ourselves. So that was kind of validating for us, like, yeah, let's try to take this idea a little further. And so we turned it into a graph, because I think it's a useful way to sort of compare and contrast different problems. Also, graphs make really good visuals for presentations, so we definitely need to do that. But I do want to kind of stress that this is a kind of a new thing, and there are intentionally no units or scale on this graph, and it's purely subjective. It's really more of a comparison tool. I'm also not saying you should literally graph out your applications. It's really just kind of developing your own intuition about when to reach for LLMs. So I'm going to try to get through this quickly, but I'm going to dive into each axis and kind of explain a little bit more so it's more clear kind of what we're talking about, and then break down each quadrant with some examples, some like familiar examples. So in the horizontal axis, we have the ambiguity tolerance, like I said, and that's, if you have high tolerance for ambiguity, that's like situations where there's really no one right answer. So in that case, like, creativity is a plus, because you have sort of these fuzzy open-ended specs where actually generating lots of alternatives is a boost. Whereas the flip side of that, right, would be a case where multiple solutions are actually not helpful because you really are after precision. So this would be where you have a lot of constraints. The specs are really rigid. Then flipping over to, this is like cutting out, there we go. Flipping over to the, vertical axis. Risk tolerance, I think, is pretty straightforward. It's where you have, so if you have high tolerance for risk, I don't know what I'm doing here. There we go. It means you have very low stakes, right? Low failure, low likelihood of a failure causing a major problem. And then the flip side of that would be low tolerance for risk, and that means you have high stakes and high likelihood that a failure could cause an issue. So then to break down the different quadrants, On the lower left is kind of what I'm calling the danger zone. That's like vibe coding your login functionality, right? Like there's security, compliance, privacy risks, and really not much ambiguity. There's kind of like only a few solutions that are actually correct in this case. The slippery slope is kind of off to the right there. That'd be high tolerance for ambiguity, but low tolerance for risk. So more open-ended, like idea of like maybe designing an API contract, but there's actually still some significant risk there of getting something incorrect. So I call it the slippery slope because I think AI can kind of fool you into thinking it's pretty good at this. And there are multiple correct solutions, but even just getting one small thing wrong can compound over time. Then this upper left quadrant would be low tolerance for ambiguity, high tolerance for risk. So there's still you have a very specific goal in mind, pretty tight specs, but the risk is lower. So this would be like just using an LLM to help you write a small isolated feature. Maybe it's refactoring well-tested code. It's something where you still have pretty tight specs, but like as long as you have sort of a human in the loop to validate, it can be pretty useful. And then the top right is the sweet spot. That's kind of where AI really shines. So this would be things like understanding legacy code bases, or doing proofs of concepts that aren't going to end up in production. Like this is where you can kind of actually see potentially that 10x benefit and learn things really quickly. So that's the framework, and now kind of the rest of the talk we're dedicating to some of the real-world examples at Livefront and kind of how they fit into that. So I'm going to hand it back to Sam now.
Okay, thanks, Adam. So yeah, let's move on to striking a balance. Three kind of takeaways that we've learned that I wanted to share, and I'll give an example for each one of these. Decomposing complex problems, trying to lock in durable deterministic improvements, and creating testable portable outputs. So I'll start with decomposing complex problems. We have a project at Livefront that's a legacy project, a large code base, hundreds of thousands of lines, and the team found that we do use a linter. We use a linter on all of our projects, but the team had kind of created some conventions that they were enforcing through code review because the linter can't check for certain things. They're just not built-in rules for the linter to check, but the team decided this is how we want to write the app. We're going to have these conventions. And just found that that tended to be time-consuming and a little frustrating because it just wasn't something that was automated, and it should be. So we wanted to figure out a way to do that. One idea we had would be use an LLM to try to help with that. Describe the lint rule that you wanted. Let the AI give you feedback. But looking at the matrix, we have this in the danger zone, so-called, or as Adam called it. Again, it's subjective. For your project, it might not be in the danger zone. It might be in a different place on this matrix. But ultimately, the challenge here and the reason we didn't go this direction is because it's really important that the linter doesn't give you a bunch of false positives or false negatives. So every time you run it, even if you're running it on the same code, ideally you'd be able to guarantee you're just getting the same results each time. So one approach we took, and where the decomposition comes in, is this task, in this case at least, is actually made up of several kind of component tasks. The first is very exploratory, just deciding on what the rules are, what the team is going to agree to. This is a decidedly sweet spot type of thing where you're just kind of brainstorming and using the LLM for that. Once you know what the rules are, we want to codify those. So we want to create them, add them to the linter, let them run automatically. That step can also be done automatically with a little bit of human oversight. Not a whole lot of risk. Some ambiguity is fine. The most strict one is detecting the violations. We just want to use the linter for that. There's zero ambiguity. Either something violates the rule or doesn't violate a rule. There's really no gray area there. None of this is super high risk, but this is probably the most risk-averse one, where you just want the same outputs each time. And then finally, Fixing violations, again, this is an area where an LLM can be super helpful, help you kind of do the initial implementation. You can imagine with a 100,000 line code base, I'm sure some of you have had this experience. You try to introduce a new lint rule, you got 20K violations. You got to decide what you're going to do. Are you going to ignore them all? Or are you going to try to fix them? We found a huge just improvement in efficiency, excuse me, by using an LLM to help us do that corrective work efficiently with, obviously, with human code review. So that's one way you can kind of achieve some of the gains by integrating LLMs, decompose complex problems. Another one is to think about just trying to lock in durable changes. And instead of having those changes just live in the LLM or your conversation with the LLM, turn that into source code that you can lock in. So another example, also in the danger zone, but again, subjective. We have a client that has a large number of web properties, and they're not really organized. So there's no consistent structure. There's no backend API that unifies everything together, but there's a lot of data out there, and we wanted to try to get structured data from those various web properties. So one option for doing that is to do some screen scraping or web scraping. And again, we're always trying to figure out ways we can integrate LLMs into our work. So we thought maybe this is an opportunity here to use an LLM, but it has similar challenges, I think, to linting. Because what we want is structured data, we really want it to work the same way every time. So that's a challenge. Now, granted, there are tools out there that do a good job of creating structured data from an LLM, but there's another factor, and that's expense. If there's a lot of data and a lot of web scraping, it can be quite expensive to just use the LLM to actually do the scraping itself. So I'm going to play a video here and just talk over it. What you're seeing, this is a screen recording from Kyle, one of the engineers on the LifeFront team, showing a proof of concept. This is using Craigslist, so this isn't our client, but just as an example, Craigslist kind of famously doesn't have a backend API. And what you're seeing on the screen is the LLM running a script. The prompt is roughly saying, open this web page, do a keyword search, create structured data from the output, and then write a Python script to do that process. So you saw the windows pop up there. The LLM is experimenting. The first one failed. It tried again, it succeeded, and now what you're seeing on the screen is two things. One, the script that Kyle's highlighting, and two, the structured data that's output. So the benefit here is now we've got a script that can do the web scraping. We no longer have to use the LLM at all. We have a durable piece of source code that we can just use repeatedly. It also has a nice quality that if it breaks, we can just run that LLM process again and kind of self-heal, because if you've ever worked with web scraping or screen scraping, you know that's kind of notoriously brittle. So it's nice to have that ability to just repair. So that's an example of just locking in those kind of durable, deterministic benefits. And the final example, totally different problem. We have a client with a large code base. It's a legacy iOS and Android app. And they wanted our help understanding how hard it would be or how complex it would be to re-platform to React Native. And at first glance, this is awesome. This is like super risk tolerant. Ambiguity could be a really good thing here. You want lots of different ideas and input on what could be complicated or what could be challenging. But after looking at this a little bit closer, the kind of initial attempt is to just, go into the source code directory, use an LLM, start analyzing the code conversationally. But that direct analysis has some drawbacks, and these are things I think we probably all run into. The first one is you get this kind of response, you guide the conversation. You're like, well, let's look for these things that I know are complicated. How much of that is in the app? And you get a response. You can't really verify it. You just get some kind of human-like response that gives you some numbers. The only way to really verify it is to go do that work yourself, and that kind of defeats the purpose of using the LLM anyway. So that's a challenge. It's also not durable. If you're like me, you've probably run into this situation somewhat frequently, although the tools are getting better, and that's just losing your session state. You're mid-conversation, something happens, you spent 30 minutes or an hour on it, and then that disappears. You have to restart your conversation. It's never the same the second time, so not durable. It's also not portable. You can't analyze any other code base with this conversation. It's a one-time thing. You get the results, and then you can't port it anywhere else. You can't use another LLM to kind of join in on the conversation. So there's some limitations with this kind of direct approach, even though it's in that sweet spot for that kind of conversational output that we get. So an alternative, instead of having that conversation about the source code itself, have that conversation about a tool that can do the analysis. That resolves all of those issues related to the durability. You can still have roughly the same conversation, but what I'm showing here is just the output of that script to look at the source code, help analyze it. That can be a very guided process where you can brainstorm or pair program with the LLM and ultimately ends up with a durable, reusable, portable script. So that was a helpful approach and insight in that case. And that's it for the striking a balance. So I'm going to pass it back to Adam to wrap us up with the final example.
And I think we're doing pretty good on time here. So yeah, those are really good examples. And I just wanted to kind of come through with our final example, which I think really landed pretty squarely in the sweet spot for us, and was one area where I think we were able to make a pretty big impact for a client using these tools. So I just kind of want to run through that. Next one, there we go. So we had a client, shocker, that wanted to create a AI chatbot, and as part of that functionality in the app, they needed this complex sort of 3D animation, like an orb, to represent the voice agent, right, when the user is speaking to it. So in this case, the requirements included a mock-up video from an outside animation firm that it had to be based off of. It didn't have to be exactly like that, but that was sort of the inspiration. And then we got words, from the client like, well, make it pulsate and undulate and things like that based on, the amplitude, so the volume of the voice coming through the microphone, but also if the chatbot is in different states, whether it's like listening, thinking, responding, it needed to behave a little differently and smoothly animate between all of those different states at any time, right? It also needed to work on both Android and iOS. So I can't, for client confidentiality reasons, show you the actual animation, but I think the old Siri animation, if you remember that and are familiar with it, is kind of a pretty good approximation. And I think it's worth just taking a minute to kind of appreciate all the little details in this, pretty interesting animation. There's, you can kind of see as the volume is changing, that sphere is sort of like deforming, and the lighting changes, and then those little shapes inside are spinning, and they spin at different rates and in different directions, kind of as the voice is going through. It's actually really cool, and something I think I took for granted for all those years when I was using it. So you might just be like, oh, hey, Claude, create me a shiny pulsating sphere filled with colorful, translucent, rotating Pringles, right? But that's not what we did. That's not what we initially did. So where we actually started was without using AI. We tried to implement this ourselves, and when I say we, my colleagues at LiveFront, Victor, using the SwiftUI canvas. And we pretty quickly ran into some performance issues with that. If you've done any SwiftUI, you may be familiar with it. But the SwiftUI canvas is really, it's CPU bound, and so it's running all this re-rendering on the CPU. So sort of the natural next step to improving the performance would be like, let's use the graphics hardware on the device. And the way to do that is, at least on iOS, would be to use something like Metal, which is Apple's framework for accelerated graphics. The only problem with that is that we don't really know Metal, or at least not experts in Metal. It's sort of a niche thing that you don't often use in most applications, unless you're a game programmer. So, and we also had a pretty tight timeline in this case. So that's where kind of, I think that in hindsight, this was a really good fit for using an LLM. And part of the reason for that is we have these fuzzy specs, like there's many acceptable solutions, and that it wouldn't necessarily matter if one of the Pringles rotates 70 degrees and not 72 degrees or whatever, it's like that's not the most important thing. We're just trying to capture the spirit of the animation and make it really smooth and look good. It's pure visual flair, right? So it's isolated, it's not critical logic. There's really like no privacy or security concerns. It's just this one-off thing used in one part of the application. And really the performance is the most important thing. Making it smooth is more important than it being exactly precise to the specification. So that's what we did. We started off using ChatGPT, eventually moving to Claude, which kind of did a better job of working directly with the code. And we tried a few things. It definitely was, there was bumps along the way. So one of those things was uploading a video of that animation that we were given from the design firm didn't work at all. So we ended up using sort of like frame by frame screenshots to help describe it. And there was a lot of hand holding still involved. Claude could create sort of correct implementations, but it would often sort of not understand how to like use the GPU effectively.
If there are any.
So it was definitely sort of, I would say we co-authored the code with the LLM to help it do a better job. And one of those techniques I think that, again, is in kind of that sweet spot is we're constantly asking it to explain what it's doing in each step and then provide a bunch of alternatives. So basically try to explore the problem space and pick from amongst the best solutions that it had to offer. Next up, after they had this sweet iOS animation and loved it, they were like, okay, now make it for Android.
So
right?
the question,
so we're like,
the question was, how did the script that was doing the screen scraping
I guess we'll use Vulkan because that's how you access the accelerated graphics on Android.
Because that would be a great question for Kyle, who wrote the script.
So,
my understanding is that it was a proof of concept, so I think it was
straight in this
pretty
direction of using the LLM.
pretty basic and could probably be made much better. But in the basic approach, one of the ways it can fail is
the team
if
at
the data that it
started
gets
with
and
that
tries to
sort of working
is
iOS
not
implementation
valid JSON.
and then
It's outputting JSON, so it can validate that JSON just to make sure that it was actually correct, at least well
that was also effective.
So
and
that's one
I think,
potential failure. But yeah, I don't know the details
as well.
Exactly how
one of those is just that starting with sort of an empty project that had the scaffolding
it's time for lunch, so thanks
was really helpful. This again, I think fits into the theme of the talk. Like getting a working Android Vulkan project up and running is a very deterministic task. Like just get that out of the way, and then sort of unleash the agent. There was also several cases where like Claude would just like try to take a screenshot and then just say, yeah, I did it, I fixed it.
So we're going to shuffle over to the lunchroom.
Not true at all.
We'll shuffle back for two talks.
Continue.
And then we'll shuffle back over to the lunchroom for networking. Is that okay with everybody? I know it's a little bit early, but I think
one particularly interesting aspect is
so let's go ahead and have
midway
lunch now,
through, like
and then
any
we're going to
big
all
client,
come
they
back
say, well,
here
we want to completely change
for the
it.
next
right?
session to start
completely change the
at
animation.
12:20.
And when
Sound
that
good?
happened, we updated the iOS implementation and then pretty much had to start over with the Android implementation. So it couldn't really like evolve the Android implementation from what it had before. It was just much easier to start over. But I would say that overall, this is a success story because it really was able to allow us to quickly see a path forward where I think an implementation, given that we weren't 3D graphics experts, would probably have been more in the terms of months versus weeks, which is how we were able to actually deliver for the clients, and ended up being a huge win for them. I think one of the major downsides of the approach, which is kind of obvious, is that we still aren't metal or Vulkan experts. So like we didn't really gain that knowledge, that sort of skill from the team. And that sort of plays into the question of, well, who's going to maintain the code, right? But I think there's also maybe an argument to be made that Claude can maintain if Claude wrote the code, that Claude can also help us maintain the code. So as scary as that is, I think that's kind of a thing that is going to be continued to be more prevalent throughout the industry. So, yeah, that's basically the end of our talk. This, I just kind of wanted to remind you, this is like kind of our idea behind it, the suitability matrix. And for us, it's just kind of, again, want to stress, been an interesting way to have a debate, even as we were putting this talk together, just talking through like where various examples fit on there. There could be other axes, I think there are, like cost and context window, and like there's all these other factors to consider when you're choosing tools. But yeah, that's kind of where we landed, and I'm really curious to hear about all your experiences and kind of whether that resonates with you. Is that the last slide? I think it is.